So let's begin. Today lecture is about convolutional network. Convolutional network is a type of network that utilize the convolution function, and I would say that the inspiration of the network itself is based on the filtering technique in image processing. And because in image processing, you can extract feature using kernel, using filter. So in deep learning, it is logical to assume that if you have the system that could learn those filters, you have a system that should be able to extract proper features that can be used to perform further processing. This is especially true for image processing, for an application that you want to process image or video, which contains spatial information. And those are the things that we will look at today. The convolutional network is a type of architecture, right? For this course, I like you to view the network as the design, right? View the network in terms of the design, that there are certain inspiration that they design the thing that way in order to make them work. For the neural net, for the convolutional network, it is designed in terms of topological processing. So instead of for the feed-forward network that we have learned it last time, when the network receives input, it has to map and compute and produce output, right? For convolutional network, it has to do so as well, but it has to do so in such a way that it needs to process the data in the image fashion, right? That means it will employ a convolutional operator. It will employ the math in order to learn what types of operator required to extract features. Okay, so let's first look at convolution operator. What is convolution? In one dimension, convolution is an operation that you compute the output based on the input and the impulse response, right? So for this one, we have W act as an impulse response, act as a system notation, and we can compute the output of this by compute the convolution between X, which is an input, and W, which is something like representation of the system, to produce output, which is ST. In terms of function, you can think of the two functions clashing to one another, and we are computing something like an energy of the clashing, right? So this is how it works. We will look at convolution in one dimension in order to understand this more. Okay, so first we have I. I here is an input. Okay, in this case, in our case, in two dimension, it will be an image. In one dimension, this would be a signal. And K is a kernel or a filter that for neural network need to be learned. For filtering, you need to specify the parameters, the value of the filter in order to design the function that you want to perform. And S is an output. In neural network here in CNN, we will call it a feature maps because each layer of the network will produce features, right? And we call that feature map because we are actually creating a map, right? Creating a map of features that will be iteratively derived and learned by the system itself. Okay, let's first look at convolution. In one dimension, convolution is a process of the two functions colliding one another, and you are calculating the overlap and adding or multiplication and integration of the two functions together. Right? Let me play this. Somehow it doesn't play out. So let me open it by myself. How about this one? This is a video it's supposed to play, but don't know why it doesn't play out. Let me open it in YouTube here then. Yeah, this should do. This is too long. Never mind that. Put it this way. Yeah, I can draw it here myself. If you compute the convolution of a square wave here with another square wave, it would work like this. It's like you are sliding this function over another function. And then once it is overlapping, for example, if it is overlap at this point, then you have to multiply it together to get the overlapped region, and then integrate it to get area under the curve. So you can imagine that at the beginning, it would be like a very small overlapping between the two, but the overlapping will increase until it reached the maximum, which is the two overlapping one another and then decrease. That results in a function like this, right? So this is a convolution process. A convolution process consists of an operation of flip the size like this, integrate by a, and then shift it by the index t, and then multiply it with the signal here, with the function here, and then add them together, integrate them together to get the energy of the overlapping, and then shift t further to get the results of each time step. Right? It is akin to moving this signal until it overlaps with another, and then see the result further. Let me try another link to show you this operation. No, this is too much. Live searching is not a good idea. Well, the link's supposed to work. It worked last year. It doesn't work this year. Let's see if it has this. Yeah, this would do. Let me share the screen to you all. Right, this is the convolution of the two signals. Here, when it overlaps it with one another, you can see that the result increased because there's an overlapping between the two, and integration results in a high value. But when it reached that, you can see that now you have fixed value because the overlapping between the two results in the same area under this result. And go on further. Right, now you get the idea how it works here. Right. So that's how convolution work, right? It works by colliding or aligning the two signals together and then shift it by time and compute the overlapping energy. You can think about it like that the two like projection onto one another, and then you compute the degree of projection between the two signals. Right, that's the convolution in one dimension as it works in signal processing. Now in two dimension, convolution work as tools to perform, like if you think about the image, convolution is an operation that you can blur the image or enhance the image to have richer details, right? By designing different masks to work with. Now how it works? It works by, if you have a mask, then you can multiply a mask to an image. Once multiplied, then you can then you can sum the result of multiplication of the mask and image together, right, within this region. Then you get the result, which is 4 here. And then you can shift the mask. You can shift the mask to the left and from the top to the bottom until the mask kind of compute for every point. And now you can see that for every point, you have a chance to perform computation. Okay, and these weights are shared for all of for every point in the image. And as you learned it last time, sharing parameters results in regularization of the model. This allows the model, instead of for each pixel, it has its own weight. For each pixel, it has to, for each round of computation, all the image has to share a certain property of feature extraction properties that are encoded in the mask. Okay, and it's used throughout the image here. This is how 2D convolution work. It works by multiplying the mask with image and then compute for each point, then move the mask throughout the image. Okay, right. So in the formal terms, convolution is a process of multiplying a signal, xk is like larger signal x, and the mask hn minus k here, and then multiply them, sum them together. This is a kind of integration. Okay, we use the symbol here, star, as to denote convolution. In terms of computation in the time domain one dimension, convolution works like this, that you have to reverse the mass first and then shift it by n and multiply this shifted version of impulse response of the mass to the signal, right, for each point. Once multiplied to the signal, then you can sum them together. This is the same story as in two dimension, but you need to think about it as a mass in one dimension, which I will have example later on. And for each n here in the output, we will shift the mass one by one, and then you get the result at each position. So let's look at some examples which should clear things up. Suppose we have xn that looks like this. This is an impulse function, a unit sample function, delta n, which has the value of 1. If inside here equals 0, that means at n equal -1. And at n equal -1, it has the value of 2. At n equal 1, it has the value of -1. And at 0, xn has the value of 1. Hn looks like down here. It has the value of -1 at 1 and has the value of 1. Sorry, it has the value of 1 at n equal -1, and it has the value of 1 at n equals 0. Right, now, to compute the convolution in one dimension, we need to first flip the signal. Right, so this is the impulse response that we have, the mass that we have. Like by flipping it, we now have this. Right, this is h minus k, and h minus k need to be shifted according to an index n. Right, according to an index n here, which is corresponding to the output y. So we start by shifting it by -2 at the pass here. Right, shifting it back to -2. Right, shifting it at the time equal -2, and then multiply this h -2 minus k to xk. Right, multiply it to xk. This is xk. Having the value of of 2 at -1, of 1 at 0, and -1 at 1. Right? Minus the 2 together, we have this bar multiplied by 0 equals 0. This bar, which is 1, multiplied by this bar, which is 2, you get Here you get 2, that bar, and the rest are 0. And then by summing this signal, this resulting data, this resulting array together, you get the value of 2, right? And then you can repeat the process, right? Move n equal -1. Do the same thing, flip shift, multiplying together, which results in here, this bar remain here, and another bar here, because you shift now with index -1, offset -1, right? And now you have this bar remains as well, and why the others are removed out, right? 0 out. Then sum this, you get 2 plus 1 equal 3, right? And then keep doing that. And that is how one dimension convolution is done, right? By multiplying the mass with the signal, and then move the mass one step to compute one output. Move again to compute another output, and keep doing that. And then you kind of compute the convolution in one dimension. And that's how convolution works. Well, this is actually the content drawn from the signal system class, right? But they are the same, right? Because when we talk about deep learning, you can use deep learning to process data in one dimension, which is signal. You can use deep learning to process the data in 2 dimensions, which are images, right? And they are the same because convolution in 2 dimensions is actually the summation of what? You can see that this is index M and index M and N of, this is output is index I and J, and then you need to multiply. Well, let's look at it down here. This should be easier to understand. This is an input image I multiplied with kernel, right? And the kernel has M and N dimension. So say if M is 3 and N is 3, then it means that you need to move, the index would be 0, 1, and 2, right? As in the example that I showed you earlier with image, that you have like 3 by 3 grid. And then those 3 by 3 grid need to multiply with image, right? So that is K here. And K multiplied with I, and I has the original index ij, and you can shift it by M and N based on the offset of the mass. Right, and that is the result of this convolution process, which is some output, okay? Okay, it means that convolution will produce output, and output would be the results of convolving image with mass. Okay. Example of convolution is, you can think of this as computing correlation, right? Correlation between the mass K and the image I, and see how both share with one another. And if you remember back in linear algebra, correlation itself is actually the projection. You are computing whether the 2 data align with one another, whether they are on the same direction with one another or not, right? Okay, so how is it done, right? If you have the kernel that look like this, you have the weights W, X, Y, and Z, right? This is done for each of the output. The value in each point would come from multiplying the kernel with an image. Like this one, this is A multiplied by W, B multiplied by X, E multiplied by Y, and F with Z. Then sum together, you get the value at this point. Then the next point would come by moving the mass, moving the kernel to the right. Now W will be over B and X will be over C. And that's why you see the values look like this. And then afterward, once you move the mass from left to right, then you can shift it to the next row and then keep doing the same thing. And then you get the results out of the convolution process, right? So this is used in creating a filter, right? Creating an image filter can be done by designing the kernel so that it can compute the difference in horizontal edge and vertical edge and horizontal edge. Blurring an image can be done by averaging the point, and then you have the blur image. But now, because the task that we want, we would not want to put the bias into the process. We want the process to learn by itself, to learn what types of processing are needed in order to solve specific problems. Okay, that means in convolutional network, the kernel will be learned. Whether we are talking about 2D kernel like this, or 1D kernel like this, right? They will be learned. They will not be specified beforehand, but will be learned according to the architecture that you design for. And it can be used on different tasks, which we will see later on different applications, which will have different architecture corresponding to those applications. Okay, but why? Why CNN becomes one of, I would say, one of the most important cornerstone in deep learning. It is one of the architecture that allow, I would say, the field in deep learning to prosper that we see nowadays, right? And because of this architecture, right, the deep learning now extend its hand to different types of applications and different types of architecture, because once we know that, okay, regularization is the key, now architecture with different regularization comes out and it works well, right? What are the key features of CNN that make it work on different tasks? There are three main features. The first one, the sparse interaction, right? The second one, parameter sharing. And the third one, equivariant representations. What are they? Let's take a look at this one by one. Let's compare convolution network with fully connected network. Okay, look from below, look from the input to the output. In fully connected network, a node X3 connect to all layer here, right? It connect to all of the point in this region. However, in the data that we process, like signal data or in image data, we know that features are often localized. Okay, like my face here is in the middle of frame, right? And if the face move, then it will localize to those specific location. But if this were to be captured in the fully connected network, it means that the localization will be hard to capture because, well, you can imagine that the pixel in the center can certainly associate with my face. But if I move, then it will be different, right? Because the face will move to a different location. And how would it be the image processing algorithm would be able to tackle this type of problems? Okay. Now, in order to localize the computation, the way of convolution allow the computation to be done only at the location close to it. Like the X3 here would be fetched only to the nearby neighbor, like only to the nearby node, in order to perform computation. Okay. Now, if we look from the above, result of one node would comes only from three nodes, the three close nodes. That means if I process speech data and arrange the data in this direction, when it detects the earlier word, it would only localize to that time, not the whole sentence, right? But fully connected version would process the whole sentence to get information just only for one time, which make things difficult to generalize as a patterns. Okay, so that means if the representation can be sparse, it can localize a certain event to a certain location, then the network can take into account of this ability and then learn only patterns that are associated with a certain location like that. Okay, and how can it capture different part of the image? We can imagine that if the feature has to pull together, and we have multiple layers like the G layer and then the H layer and then input layers. The deeper the network, right? The more generalizability it has, because let's say G3 here would cover H1, H3, and H4. These in turn cover a larger receptive field, right? So that means if you have a deeper model, then surely your processing pipeline should be able to handle the feature of the whole image. For example, like this one. Because image features are often localized to a certain location. If what you want is, so what you want here would be different from what you have here and here, right? If you want to capture the feature related to the pollens of the flowers, then what you want would be in the middle, not in here, which are nothing at all, right? So you can see that sparse interaction allow you to capture different location, to localize the processing into different regions of the image. That is the first one. Secondly, the second one is in terms of parameter sharing. This is one of the key regularization feature in the convolutional network, which I don't know if it is like, it is a chance finding that the researcher find this technique, because we the convolution has been there all along for a long time, and they just like picked it up and then use in the neural network, or it is like a clever scheme to that they come up with, but I would lean toward the first because the technique is there already. With certain adaptation, it works well, actually. Okay, so comparing between fully connected, the parameter that is used to link X3 and S3 is solely dedicated to X3 and S3 only. But in the convolutional network, when you compute the convolution of one layer to another layer, like compute the mass will share the weight. So for example, in this case, you can see that S2 used the HDH from X1, X2, and X3. S3 used from X2, X3, and X4. The middle one will be the same. That means the weight will be the same, right? Because you kind of have just one mass, and then you use it all across the signal. It's like this. It's like you have a vector like this, and what you are doing is to learn this mass, 1/3 mass. This 1/3 mass will move and then perform computation of each point. Like for this point, it will take in data from all these 3 nodes and then compute the value here, and then move to the next one, use the same way to perform computation. This region is called feature map, right? And this is the kernel on the mass, and this is input that we have, right? So the parameter sharings allow the kernel to be learned, and then use and use and apply throughout the image, like this figure. Right? So that means the small mass learned in the corner there will be processed the whole picture, and then produce feature map that you saw on the right. Okay, and it will learn by itself. We did not specify how it should learn. It will need to learn by itself on what types of features are important in order to achieve the task, right? Based on the backpropagation algorithm. So parameter sharing allow the network to learn feature maps, and these feature maps allow the network to learn the kernel that compute the feature map. Each feature map will be represent certain aspects of image. So one mask will produce one feature map, right? One mask will produce one feature map, and then used throughout the whole image. Right. This is parameter sharing. Right. The equivariant means that you can shift before applying the function, or applying the function and then shift. The output should stay the same. Okay. Right. So these are the. What is the last one? Right. The last one is like the operation that that occur earlier can be arranged in terms of order. So in terms of the convolutional network, because we have like multi-layer processing, right? We would need to arrange a network to be deeper, right? To have like multiple layers. Each layer will learn the work that it has to do, and the shifted version, or I would say the the processing version of certain layers of the output layers would comes after the convolutional, the processing layers. If the input is modified, this will equal to modifying the output. Right? This is the equivariant aspects of convolutional network. It means that it has a certain linearity, and it makes the results combinable. You can combine the results together. Right? To understand this more, well, I think if you want to understand this more, I think you should look at the concept of linearity in the signal processing, and which is about superposition and the equivariant here. So in terms of a simple explanation here is like if you have a shifted version of input, you have a shifted version of output, and that means you can arrange the processing to be done after the function, after the convolutional process, or before the convolutional process. It doesn't matter. Okay. And also, suppose that you have image that is shifted. Right? The results will equal to you shift the output. Okay, you shift the output. It would not kind of produce different things. Right? It will not produce entirely different things. It will produce the same output, but shifted in the location. Okay, then when you combine the results together, it will still look the same with the same aspect of image that were captures. Right. So these are the three regularization aspects, three regularization aspects of CNN that make it work. Right. Another thing that is added to CNN, which again regularize the network, is the concept of pooling. Okay. What is pooling? Pooling is, you can think of pooling as a summarization. It is actually a process that summarizes the feature map, which has the same dimension as an image, to be lower resolution. So in terms of processing in convolutional network, right, the layer would perform convolution. After performing convolution, then certain activation function will be done. This is at detector stage. Then at last, the pooling function will be used to reduce the dimension of the image. Okay, so when you have input layer coming in, you get convolutional stage, and then detector stage, and then pooling stage. Right. So in terms of layer, then you have all three layers here to denote a certain processing unit in convolutional network. Okay, what is the purpose of pooling? To summarize the data or compress the data into lower dimension. When you compress it into lower dimension, it means that you are trying to look at a larger, right, a more coarser features. Because let's think about this. Suppose that what you see on the screen right now has low resolution, but you have to scale it out to be at the same size of your screen right now. What would you see? You will see image that is blurred, pixelized, or not nearly as detailed as it should, right? But you can think about this as when you look at something. If you look at it too closely, or if you want to detect just a general sense of it, like think about when you wake up in the morning and then you look at, and then you still have not cleared up your vision and look at something and you still recognize what it is. How can you be able to do that? Right? It means that you have recognized certain shapes, certain features of those objects, of the things, and then translate those things in your brain into that object, and recognize those as objects. This is the same thing. So instead of detecting only the fine level at the high resolution, or you can dump it down, right? Dump it down into a coarser resolution, which represents something that is larger in terms of the scale, right? Because when you have like comparing between 512 to 512 image and say 16 by 16 image. The 16 by 16 image, actually, if you kind of compress it down, it will have like a blur level of the larger image. You have like the outline of the larger, more detailed image, right? So that is the purpose of pooling, to reduce the dimension down, so that it can learn something that is in the larger scale, maybe pattern in the larger scale. Right? So, right? For example, if you want to capture the face here, then the camera, if the camera want to have algorithm to capture the face here, it needs to be able to track the feature of the face, but it doesn't have to be the whole feature. It can just track the general shape of the face. Like, okay, there should be some hair here, and there should be certain contrast to create a face. There should be some point here to be the eye. It doesn't have to be perfect to be able to track, and that is done by having this cluster feature. Okay, so it only need to have all the detail to work there. But again, we will not tell the system what types of feature it needs. Right? It needs to learn by itself, and we just creating an opportunity for it to learn cluster level, more abstract features. Okay. Pooling, there are different types of pooling, right? This is called, the first one here is called the max pooling. For the max pooling, the result in the pooling stage would take the max value, like this one. This is like from 0.1, 1, and 2, get 1. For this one, you get 0.2, 0.1, whatever, you get 0.2 here. But this is max pooling, okay? Right. So there are different types of pooling. For example, this is max pooling versus average pooling. Think about max pooling as taking only the maximum value, or taking only the highest activation out of the image, out of the result, while average pooling take all the value. Okay, so max pooling would be better for nonlinear features that you want to detect, like the edge, while average pooling would be better if you want to detect the content in the image. Right. So here for this one, using average pooling, you get average of this green, of this orange, of this red, of this blue, get this value. Max pooling, you get this 21, which is the max value. It's easy to do. Look at here, 12 here, right? So you get the kit of it, right? Okay, so this is how pooling is done. Pooling can be done and incorporate with different architecture as well. For example, you can create a pooling of different variation, right? Create a pooling of the rotation of the image. So now your network should be able to take into account of rotation as well, because now you have like multiple layer of data that rotate from the input with lower resolution. Okay. Pooling also accompanying pooling, not just summarizing like this, because you might see now, why not we just shift the mask just like earlier, and then we will have like very detailed point instead of having 4 from having 2 by 2 from 4 by 4. But the point here is to get the 2 by 2, to get the lower resolution, because pooling itself is a type of downsampling technique that you want to reduce the representation size, so that once you reduce the representation size, the parameter size, it would represent a coarser level of the image. Okay, the technique to perform this, there's this one called the strided convolution. So instead of doing the pooling later, you can combine them together and then having a parameter called the stride. The stride will compute convolution and then skip certain point to compute another convolution. So instead of computing convolution of every point, then it will just compute convolution of some point, which equal to compute convolution and then perform downsampling. right? In CNN, in the CNN layer that we'll see later on, there will be a layer that you can specify, convolution layer that you can specify the stride, whether you want it to like skip by one, or whether you want it to like use every point. And these are fine. This is the stride equal 1. The mass will be used for every point, and the stride equal 2 means that it will skip 2 positions for each mass. Okay, the network can be designed so that it has a fixed size, like this one, that you have convolutional layer, pooling, convolutional pooling, and then reshape into just one-dimensional vector, and then perform fully connected to compute the class, right? Or you can have the variable size by, you can see the difference, it's here, right? So you compute the convolution down so that you have the output of pooling would be reshaped into the smaller vector here, because everything would be pulled down into just 3 by 3 grid at this point. Comparing to the first one is like you reducing it by the stride of 4. This one is like you fix that, okay, this one needs to be reduced to 3 by 3 and 64 feature maps, and then use it to perform computation. That means you can now have the variable of the input size, because it doesn't matter, it will be reshaped to this layer anyway, right? You can have multiple paths to connect to this one. Or you can have the last design, that is, you have a convolutional layer until the end, right? Until the end, have the convolution and dump down to the last one, which this is not, well, some design use this, but mostly the design of convolutional network would separate between the classification part, which is the fully connected, and the feature extraction part, which are usually the convolutional part for the image. For text processing, it will be the RNN and fully connected as well. You will see about that later on. Okay, we will look at some example. We should certainly clear the pictures here. So because look at it this way, well, this is input image, then perform convolution. You get the output of convolution as 256 times 256 times 64. That means you have like 64 feature maps. That means you have like 64 kernel to produce the output. And the output is sample by 4. That's why you get the resolution of 64 times 64. And then convolution again, you get the same dimension, equal number of feature maps. And then sample down again, striding, you get 16 by 16, arrange it into a one-dimension vector, and then put it into fully connected to perform classification. This is for fixed size. For variable size, we have this size of image, and then doing the same thing, reduce again the same thing until this point. At this point, we did not specify that it should be stride 4. We kind of resampling the data into just 3 by 3 times 64 grid. That means the whole image should be now pulled into just 3 by 3, right? Whatever the size here is, right? We pull to 3 by 3 grid, and then use these to perform classification. And that's why it's called variable size. The size can be changed, whatever, but the size of image up here can be changed, down here can be changed, but the above will stay the same, fixed to 3 by 3 grid. For no fully connected, now you can see that these are only convolution and pooling until the end, right? Which, well, in order to do this, you need to have like a really deep network to take into account of this classification relationship as well. Okay. Now, in terms of processing, now you will see that. Well, but if you use 3 by 3, the size of the convolution here would not be 256 times 256, right? Because you have like the perimeters of the image, right? The location around the perimeters of the image that does not contain 3 points. It contains only like 1 point or 2 points at the rim of the image. How to process that? Right? In order to help in processing, there is a technique that is called zero padding. That means, so with no padding, the convolution would produce a result that is like smaller and smaller to the center, which is not the thing that we want, because we will lose the information at the rim of the image. What we want would be to maintain the same size. In order to do so, you need to pad certain zero to the side of the image, so that the computation would take those zero in computation as well at the size of the image. And you have like the same data points for every layer that you perform computation. Okay. Right. So in conclusion, in terms of convolutional network, in terms of the technique itself, you can see that convolutional network composes of performing convolution, right? Performing convolution, having the mass convolve with the image and produce here, each of the sheet here that you see is called the feature maps, right? Produce the resulting feature maps, right? These will be learned, right? The layer here, the mass will be learned, and the feature map would be produced according to those mass at each layer. You can have like 64 of them, 200 of them, whatever, depending on how many layer of feature you think that is required. Then, right, these multiple feature map will be dumbed down using the pooling or subsampling, right? Will be compressed. Different strategy will be used to perform convolution. We will use to dumb the data down. Right? If you look at, for example, the text data, convolution is also used there, but it needs to have a certain way to pool the data, not the way that is in image processing. Right? So for this one, well, think about pooling as reducing the size or the dimension of this square. You have a smaller one, then doing convolution again, you get another point, you have a smaller one as well, and then reduce it further and further until you get the result here, and then strengthen it into just one vector, and then put it into fully connected to perform classification. Okay, you can see that the dimension of the data reduce, right, further down the line, right, by subsampling and pooling. And also by doing so, the feature that you should be able to extract from the image would be more abstract, would be at the higher level, like at the whole image, at the whole region. Okay. Right. So the process like this, you got pull it down, doing sampling, subsampling like this, and max pooling would pull just max value out of each region. All right. Okay, let me take a break here. Let me take a 15-minute break. And afterward, we will look at the application, the design, and some examples in the lab sheet. Okay. We will start again at 7:15. All right, I'm back. Let's wrap things up. Let's look at some examples of the convolutional neural network here. A convolutional neural network is used to process image, right? For example, if you want to create a classifier that could classify the image into the type of the image, like this is a car, then you need to have the CNN can be designed this way, that you have the convolutional layer, the activation function after passing through, say, LeLU, then perform convolution again, passing through LeLU to kind of creating the nonlinear processing. And then you perform pooling to reduce the image dimension, the processing dimension. Then perform convolutional LeLU, and pooling, and keep doing that until the end, and performing the FC, the fully connected to create a classification task. And then this can be done and then create, and then you now have a model that could be able to learn the image features, and then it can perform classification like this. Let's look at some example here. This is example from the Imagenet challenge. This challenge is was designed to facilitate the development of deep learning in image processing. The goal of this competition is to classify the object classify the object in the image into classes. Okay, and there are many participants. What I will show you here is the results from back then that use convolutional network. This one is AlexNet in 2012. Another name is Supervision. This model in 2012 used the stochastic gradient descent trained on to NVIDIA GPU, and it used a week to train. But you can actually do it now with the current GPU a lot faster. Okay, so this is a mesh, and then you have convolutional layer, 5 of them. Each convolutional layer consists of banks of 3D filters, and then apply the pointwise nonlinearity. That means you have certain activation function. And at the end, you have the fully connected layer. If you were to extract the feature map and then view it, you can see that feature maps feature map that is produced is actually capturing a certain aspects of image, like the edge of the image and others. Okay. AlexNet outperformed the competitors back then in 2012, and it's like the start of deep learning era since then. Right, so it has the lowest error back then. Okay, this is results of Imagenet in this year. We have like since 2012 till now, we have GoogleNet and ResNet, which already surpassed human classification. Okay, let's look at VGG, which is a good starting point for convolutional network to understand that. VGGNet consists of 16 layers. It's 16 convolutional layer, excluding pooling layer. And the mass is only 3 by 3 mass. So it will perform 3 by 3 mass convolution on each layer. And in total, there are 138 million parameters to learn. Okay, and there is actually a pre-trained model which you can download and then use it to test out. Right, so from this image, you can see that the VGGNet has convolutional layer in consecution and then pooling. Like convolutional layer to convolutional layer and then pooling. Each pooling here will reduce the image dimension down, the data dimension down until you got to this point. Then the data will be stretched into just a vector and then perform fully connected to produce the final probabilities. Okay. And this is for the VGG, which consists of like a layer of convolutional and pooling layer, and at the end, fully connected layer. In 2015, we have the proposal of the infamous residual net, right? The ResNet. Right? The ResNet used the residue, the skip of the connection. So comparing to VGG, we have a multiple layer of convolution, but in the ResNet, instead of having just multiple layer of convolution, you have a skip as well. What is the purpose of this skip? And the purpose of this skip is so that the propagation of error at this point could propagate back to the earlier part easier than passing through the network here. Because passing through the whole network here, the error would kind of be modified, for different layers, and that is okay for VGG. But in order to increase the performance, you need to have like a bypass of the error so that it can bypass to the earlier layer and then contribute to the feature training of the earlier layer by having this residue, this skip connection between layers. This skip connection is actually just adding this. It is actually very simple. Adding this to the output, just that. Just draw a line from this point as input to this combination. And that's also mean that error propagation would need to be worked backward as well. That's you have error here, it need to be distributed into this path and also to this path to learn here. Okay, so this is the residual net, which work very well in terms of performing image classification. Now you can see that for image classification, it consists of the layer. It consists of the layer that perform feature extraction and the layer that perform classification. Okay, the same goal for this one. You have FC at the end, and you have the layer that perform feature extraction. Okay. Now you can cut this network, say the VGG, cut this network by here, remove the part that perform classification and replace it with something else, which will create a very interesting network like this one. By adding the results here to the RNN and then train the network, right? With here you have image, you have pre-trained VGG, and then you have an image and the text. You can then train the model again so that it learns the relationship between image here and the text, right? And then you can have a system that could perform image captioning, right? Like this one, it will produce as a girl in pink is jumping in the air. Actually, last year, I got students work on this. I turn it here as well. Work on this project, right? To create and you can see that because you have like two parts here, the one part dealing with feature extraction, another part and the output here will be used as the initial state for the RNN to perform text generation, which we'll look at it next time. And text generation which will involve with like generating a description out. And this like black dots jump over the bar, and you need to have like a large data set, a wide variety of data set for it to be able to do that. And there are like a weird output as well that it produce, but this just are the best of them. You can use a CNN to perform something like segmentation, tracking, and others by utilizing the feature extraction ability of CNN and combining it with a different strategy to perform image processing tasks. All right. Now let's take a look at the lab, and then we'll see some steps that you can build CNN using Keras, a very simple way to do that. And I also post the assignment that you need to do, which is simple image classification, right? It doesn't require that much of the computation comparing to the other course, I suppose. Okay, let me share. Let me start Jupyter notebook and share it here. Okay, I need to copy lab 8. Okay, it's here already. Lab 8. Yeah, I forgot the earlier part. So in this one, we will use the CIFAR 10, right, to do the demo. CIFAR 10 is 10 class image classification. Got like these classes, 10 of them. We'll just use Keras to load the data. You need to have Keras and TensorFlow installed in order to make it work here. I already did. So here in the code, I loaded CIFAR 10 from the dataset, Keras dataset CIFAR 10. And this is just to print, and it should show the image, some of the image out. It will download the data. .170 megabyte of data. done. And these are examples, right? The size of image is 32 by 32, very small size, but you can see the outline and can guess this should be a frog. It should be a truck, right? A boat, a horse. So let's train the model then. And we have like bird, right? Okay, no peacock, but well, this should be bird, right? I suppose. And here are the train Y, right? These are the labels of the data of each of the data there. And we need to first convert it into category. I use two category code. You got the Y in the one hot encoding style for train and for test. And then just to scale the X value to 0 and 1. We got 10 class. Then here is the code. Well, you can build. Well, I actually do not limit the use of different API. That means if you want to use PyTorch to do the reassignment, I'm fine with that, right? If you want to use Keras, it's okay. If you want to use any other interface, it's okay, right? As long as it's built the model that we want here. Right. What I will show you here is the way that you can build the Keras image classifier using sequential method. Right. You can use different methods as well, like the model API, which in that case you can specify the path of the model, which is a little bit more advanced. You use that in doing the Siamese neural net, like creating like face verification model there. And for this one, well, I just import a bunch of layers and then use the base model sequential. Now we have an empty model. Then iteratively, I will just add the layer starting with this. This is convolutional layer. I want 32 feature map and using the 3x3 mask, input shape, and then using LLU activation, using padding to be the same. And then just add them. Then I also put in dropout as well. That means for each of the mass, each of the point, it is possible to be dropped. Okay. And I add a bunch of them, right? 32, 64, and then also performing max pooling to reduce the size down, pooling again, and each of these I increase the number of features so that it has a higher chance to detect different patterns in the more abstract level. Right? These are the design choice. You can experiment with them, but keep in mind that each of the number that you choose actually has certain meaning. For this one, the reason that I choose the number of features like this, it means that I allow the model to have more patterns at the higher level. Okay, at the coarser, at the low resolution. I allow it to have like a more combination in terms of the model there. And then performing flatten. Flatten means that at this point you may have the convolution layer from 32, right? Dumped down to 16 to 8x8 to 4x4. Now by flattening it, you now have like 1 time the length. And then that would be fully connected with the dense layer, right? And then dense of 1024 dumped down to 512. Why doing that? Well, you want to reduce the data rate because you want to perform classification. Different types of model require different treatment. If here what you want is to encode, it might be different from this. But because what I want here is to perform classification, then that's why we need to have fully connected down here and down to the dense of 10, the number of classes, using the softmax activation at the end. All right. And this model has how many parameters? 3 million parameters. Okay. And it performs max pooling, right? I did use the max pooling layer here. Okay, max pooling 2D. And then we need to compile and train the model. And in order to do so, you need to put in the optimizer, like what you learned it earlier, and also put in the types of optimizer that you want to use. And what I use here is accuracy to monitor to be the validation metrics that we will look at. By compile, it means that we are now have the model ready to be trained. It hasn't been trained yet. We just specify just like compiling a program. You now have the compile program, but have not executed it yet. Right? So now the program is ready to fit with the model is ready to fit with the data. Then the fitting process, putting in the train data, I use test in terms of validation here, and then put in this number of epoch, the batch size 32, right? That means you will train by 32 sample. I put in only 4 epoch because it takes some time to train the model. Now it takes some time. I know it should be something coming up. I don't know why it doesn't show up. Let me check what happened. Yeah, my computer is slow. Bear with me for a moment. I have just a slow GPU with me this time. Okay, now you can see loss here that it reduced, accuracy increased, but this is just 0.22. For 10 class, the chance is 0.1. This is better, a little bit better. You got 0.22, 0.23, but not that better. Right now we cover all the instance, go to another epoch, the weights are updated. Then this epoch, you can see that here it compute the accuracy of each batch and the loss value, and also accumulate the gradient to update the network. After some time, it should finish. I need new GPU. Oh, actually, I need the fast one that's not here. Okay, now it's 48, right? A bit better, right? You need like a number of iterations for this to maximize itself. And you can see here, this is the training loss, and validation accuracy now has become 0.47. Okay. Almost there. Actually, this example can be run on Colab. That is used just only a few. If you limit the number of epoch, it should be fine. Right? Come on. The one I gave you is to perform digit classification, simple digit classification. You can try it out by yourself. Design your own CNN to get the job done. Okay. By designing your own CNN, I mean you need to think about the number of parameters that you will use. Okay, and the reason why as well. And that includes pooling. That includes the size, the number of feature map that you want, the mass. Okay, that's done. Now we have here like 0.54, 54%. It should be better, but like 10 iteration, 10 input should be better than this. Okay, the way to save the model, you can save it as H5, and then you can load it. You can load it up. Click too fast. And you can load it up after saving. Come on. Load model. Yeah, the name is different. Then you can the model out here, and then you can here use it to evaluate the accuracy of the test set. Here, the default. This is the way that you can train the model from scratch. Okay, but you can also use the pre-fit model. There are pre-fit for the VGG, for the ResNet. For the VGG, the model will take in 224 by 224, and then it learn each layer down here. We don't need to rerun the model, because here we can import the VGG. Size is 55 megabyte. Now, because the size is 224, we need to have different data set. For this one, I have this stored on my computer. This is the bird data. Here, I save it as the bird.png. Let me show you that. But the bird.png doesn't come up. Why? Bird.jpg. How come it doesn't show? Oh, I probably turn this off. I need to turn it on. Bear with me a moment. Need to go to the website again. CH. What? Right. This should do. Okay. Forgot to turn the permission on. Here. 3090. Not buying it now for sure. Too expensive for now. Let's wait next year, after Ethereum change to 2.0 maybe. Here, the picture. Okay. And let's visualize the feature maps. Once you put the input in, what happened? Right. This is a way to extract feature map by get the weight of. Well, I will not explain every part of the code though. So what I do here is to just get the weight, of the layer, and then print it out. These are the layer names, and then once we know the layer names, we can extract it. Well, we know that, okay, we get a layer 1, model layer 1 here, convolution 2, and then get the weight out, normalize the filter, just show it out. These are the filters that are learned at layer 1. Okay, the white value indicate high value, the black one indicate low value. Now to view the feature map, we need to again extract layer. Okay, extract certain layer, print the layer name, and then we need to put in order to get the feature map, instead of having the output as the final output, we need to reconfigure the model so that it produces the output as the layer 1 output, as just that layer. Okay, and with that and then what I did here is to load the image, and this is the picture of the image. convert it into array, and then set it into the proper dimension. Because this is just one image. Usually, Keras will need to have a certain dimension. You need to have like the first dimension as a number of samples. I don't have that here, so I need to add one dimension as the dimension to zero in. Then pre-process it to scale it for VGG, perform prediction, and then you get feature map. This is just to plot feature maps, and then you can see that the feature map on the first layer would trying to capture different part of the bird image, like the background here, the difference between the belly and the rest, right? It's interesting. The head and the toe, the legs part, yeah, and different part of this were captured by these feature maps or the edge here, right? And these are learned automatically, and you can view them here. Now let's look at different layer. Right? This is just to perform like a looping to look at different layer from the detail layers to, this is from block 1. This is from block 2, which you can see that, well, it's just similar to block 1 because they have not been scaled yet. But it's from block 3, from block 4. Now it becomes more abstract because of the pooling process and the convolution that produce the feature maps. The feature map become a little bit more abstract because it like trying to see the region. Like this one, you're trying to capture patterns from the above, whatever that pattern is. And the more you go through that, you can see that you try to look at like just a general area in the image. Okay. So now in this lecture, you have seen different, not done yet? Yeah, this is done. Okay. You have seen that the convolutional network relying on the ability to share features. It relies on the ability to take into account of the local part and then spread it out in the feature maps, learn different patterns on different layers. And then you have a way to combine them as well, right? So your assignment for this lecture is to play around with convolutional network and come up with your own design, whatever design you want. Just being able to classify the optical character recognition, right? If I OCR doing the OCR, the digit, just that, really very simple task there, right? If you want to play around, just try to rotate it and then create some of your own interesting network and then put it into the report, save it as PDF and submit to the lab LEB2. Okay, that's it. Right, I look forward to see your results there. And you got 2 weeks to do this assignment. All right, any question about the CNN here or the assignment? All right, if nothing else, if you have questions, post into the group. If you have like interesting paper about CNN, about architecture you want to share, please post it into the book, into the group, right? I would love to look at that. Okay, well, for today, let's call it a night. Have a good night, everyone. And hopefully you enjoy this assignment. Just play around, right? There's nothing wrong with any design, just you need to have certain explanation. That's it. Okay. See you again next time. Next time we'll again looking at another interesting architecture and then try to make sense of them. Okay. For today, have a good night. See you next time.